Good morning all. This is Mrs. Arshika, working as an assistant professor in AA and DS department. Subject code AL3451, subject name Machine Learning in the Regulation 2021. Today we're going to discuss the topic Vapnik Servonics, that is VC dimension. Before starting the topic, just imagine you have two students, one memorized answers, another understood concepts. Who will perform better in new questions? The answer is obviously the one who understand. In machine learning, this idea is measured using VC dimension. VC dimension is a measure of the capacity of the hypothesis set to fit different data set. It is introduced by Valmir Vapnik and Alexei Servonics in 1970. It is a way to measure how powerful or flexible a model is. It tells us how many data points a model can perfectly classify in all possible labeling situations. It tells us how many data points a model can perfectly classify in all possible labeling situations. A hypothesis set shatters a set of points if every possible labeling there exists a model that classifies them correctly. Example, if 3 points can be separated in all possible ways, VC equal to 3. If 4 points cannot, VC remains 3. VC dimension is expressive power. Higher VC, more flexible but more risk of overfitting. Now the question, does a higher VC always mean better model? Obviously no, it may overfit. In above message, in above diagram, the 3-point cases for 3 points in a 2D plane that are not collinearly, there are possible labelings. The 8 cases shows in the image demonstrate that every straight line can correctly separate every possible combinations of red and blue labels. But in case of 1 and 8, all points are the same color, all red or all blue. Cases 2 to 7, various combinations where one point is one color and the other two are another color. Bounds of VC dimension. VC dimension also tells us how much training data we need. Upper bound grows logarithmically with VC dimension, meaning as model complexity increases, required data increasingly slowly at first. Lower bound, minimum number of samples must increase probability. Example, simple topic need few example, but in case of complex topics need many examples required to classify. Applications of VC dimension. Where do we use VC dimension? Not just theory, it's applied in real machine learning system. In neural networks, it measures complexity based on layers or parameters. In SVM support vector machine, it analyzes margin and classification ability. Decision trees estimate overfitting risk. Multi-class classification, regression problems where catch them because VC dimension helps compare models before training them. Shattering. It plot points and shows all possible labels and demonstrate separations. In capacity metrics, flexibility of the model, low capacity, high capacity. When comes to the model complexity, low VC dimension, it shows the simple model. In high VC dimension, it shows complex model like neural networks, parameters, etc. In sample complexity, more complex model needs more data. When in the VC dimension, complex models plus small data equal to overfitting. The next topic is probably approximately correct PAC learning. In this scenario, suppose a doctor diagnoses disease with 95% accuracy, 99% confidence. Would you trust them? Yes, of course. That's PAC learning. PAC probably approximately correct. Probably means confidence. Approximately small error goal. To find a hypothesis that is correct most of the times with high probability using limited data. PAC tells us when learning is theoretically possible. Why the concept of PAC learning? PAC learning provides a mathematical framework for evaluating learning algorithm. It finds the relationship between accuracy, confidence, then sample size. Higher confidence need more data needed. In PAC helps designs algorithm, analyze performance, predict generalization ability. In sample complexity, number of training example needed to reach desired performance, desired accuracy, confidence level, hypothesis complexity, learning multiplication with the 60% accuracy and 100% accuracy for many example, strict requirements, more data requires. In hypothesis space, set of all models algorithm can be chosen from small or large space. Small space means less flexible, less data needed, may underfit. In large space, more flexible, needs more data, may overfit. Challenges of PAC learning. It find finite hypothesis space, known distribution and existence of true function. Real world rarely satisfy this. So the real world difficulties, data distribution unknown, noise presence, infinite model possibilities. PAC is theoretically guidelines, not direct solution. PAC learning is like a physical laws, perfect in theory, approximate in practice. Finally, VC dimension is measures model complexity. PAC learning is measures learning feasibility. Sample complexity means measures required data. Thank you.